So in this lecture, we would like to give some more examples on the generalization of L1 regularization. First, we talk about other type of regularization. We can also use other norm, LQ. All right. Suppose Q is a real number, a real number that is bigger than 0. Okay. So if we if we have a vector beta for beta 1, beta 2, beta p, right? You have p components. Okay, so these term here, so these term here, you the sum of the absolute value of bj to the power of q. So this is like the norm q of the beta with the power q. Okay, so remember the p norm of a vector. The p norm of a vector is x1 to the power p, x2 to the power p dot dot dot, right? And then this summation, and then take the p square root, the p's root. So this is called p norm. Okay, so when we generalize to use q norm with the power of q, these will also have effect on the solution of the problem Lq-regularization. So here we have a sketch of how the LQ norm. I don't want to use the term norm here. So basically, so we focus on the yellow term, this function, this penalty, and what we plot here is actually the region for which this summation, this summation is less than 1. Okay. So you see that, of course, when q equal to 0, that is the typical 2 norm. When q is 1, when q is 1, that is the typical L1 norm ball. Oh, sorry. Okay. And what we have in the literature is when q is strictly less than 1. For example, q is 0.5, q is 0.1. First of all, I would like to state this fact that the Lq-regularization has been used to obtain sparse solution as well, just like the L1 norm. It has more desirable property in the sense of recovery rate. About the accuracy, people can prove that is more superior than L1. All right. But the thing is, I would like to mention that when we dealing with Lq-regularization, the regions here is no longer convex. It's no longer convexed, and that makes a numerical method that applicable to the problem can be it can be more difficult. Okay. This is just to put a reminder, just a simple note that that people have been using Lq regularization as well. And the reason why it can still promote the sparse solution is with the same reasoning, right? So if you minimize some function of beta subject to Q norm, all right, less than 1. So again, so if the contour of your cost objective, right, you're looking for a point where it lays on the unit norm ball and also it touch the contour of the curve, you see that it will be likely, it's often the case that the touching part here, it falls into the vertices of the norm ball. And when you hit the vertices, it basically means that your solution, some of the components are 0. And that means sparse solution. Okay. I would like to maybe go back to L1 regularization, but then give examples that can be applied. How can you introduce L1 penalty to many kinds of statistical estimation? Okay, with the one fact in mind is that the reason why they put L1 regularization is because they want to promote sparsity in the solution. But that sparsity solution, now we can talk a little bit more about the structure of the sparsity. Okay, sparsity learning has been around for like almost a decade, right? More than a decade, more than 10 years. There's a good book in, given by Hasty, who also the author of statistical learning textbook as well. If you look at the keyword here, logistic regression, okay, and that's one of the simple technique for classification, binary classification. Not sure if you have heard about graphical modeling, okay? But if not, I'm going to give some simple introduction here. PCA, principal component analysis, support vector machine, or linear discriminant analysis. The method, actually most of the method will be discussed again in this class after my part. Ajahn Vijayakon, Ajahn Shanchai can give a very good lecture at that, but I can give you a very first introduction. Probably you don't know the detail of this method, but I just would like to demonstrate that how they can promote sparsity of the solution of these model parameter. All of these statistical models lies with the same principle that eventually when you wanna estimate the parameter, you will end up with a problem of minimizing some loss function, okay? And then, for example, the logistic regression, that's one function f, okay? For graphical modeling, that's another function f. And then, so what these methods lies in common is that the way we add the penalty term, because of the goal of we would like to promote sparsity in the solution. Okay, let's see the first example. Logistic regression is a problem where it's a classification. It actually its purpose is for binary classification. You would like to learn a model that actually that is actually the probability profile. Okay, so you have the regressor. Sorry, you have the predictor X. Okay, and you have the response Y that are binary, either 0 or 1. Okay, and in logistic model, you model that the probability of Y equals 1 given X is this logistic function. Okay, it's a CDF, all right, of logistic function, and then in the model it modify the function in such a way that in the way that this exponent here becomes affine function in X. Okay, so the problem is there's some details behind, okay, that I don't want to go through the detail, but basically remember that if you have the probability of Y equals 1 given X, of course you get the complementary probability, which means you will get a Y equals probability of Y equals 0 given X, right? Because that's 1 minus P of Y equals 1. So the problem in the logistic regression is that to apply the maximum likelihood principle, how can I find the optimum beta, the parameters here, the model parameter here, such that when I have a pair of predictor and response, all right, think about I have the what, I have the profile of I have a pair of profile of patient, right? And the patient have symptoms. either 0 or 1, right? Either they are normal or they have a symptom. And X, the predictor, would be the health profile, like the lab test results or things like that. So you want to develop this model, which means you want to develop this function. You want to optimize beta, okay, such that these probability function match best with the data profile. And that's the process of maximum likelihood principle. Okay, what you do is you maximize the log likelihood function. Log likelihood function. Okay, so the detail will be given by lecture from Ajahn Vidyakon later, but I'm just simply give you a meaning. All right, but then the next step is, of course, what in many applications where the predictors are so many. Suppose like you have x1 to xp, and the I mean, in application, the dimension here can be like in order of 1,000. And then you don't know yet which predictor is relevant in order to classify the response Y better. That's why you introduce the ladder term. Okay, you apply the L1 norm on the beta, so that you aim to get the sparse beta. And of course, the entries of in the 0 entries of beta will correspond to some predictor, right? So here is x3. So that's why when you solve this, so now go back, remember that whenever we have this problem, of course you can control gamma to be high, to be, you know, high with a certain degree, and then then you get a sparse solution beta. Okay, and so having that result will allow you to interpret the model that, okay, not only that I develop a logistic regression, but I can also use the solution to explain something, to interpret about my predictor significance. Okay, this problem is again mature, already well done, can be solved in R and in MATLAB using GLM. All right, this is called generalized linear model. Okay, all right. The next application now is about graphical modeling. In the problem in this application is where you have you have several variables. This is about this is a problem about model inference. Remember that the problem in machine learning can be regression problem, classification, right? I mean, in supervised, right? In supervised learning, it can be regression, it can be classification. And we also talk about a broad group of problem where the goal is not only that after you have obtained the model parameters, but you want to use model parameter to infer about something, to conclude about some pattern that hidden in the data. All right, so graphical model has a problem goal in that sense. Okay, learning the parameter is the first primary result, but the byproduct is you can get the model parameter to explain this. Okay, so this is what I'm going to explain is that you have n variables, x1 xn. Okay, so these xn, these n variables are random variables. Okay, what you would like to draw is that you would like to get information about conditional independence relationship among the variables. Okay. Remember, so this is to remind that, okay, what does it mean by conditioning independence? Suppose you have x1, x2, x3, x4, all right? So if I want to verify if x1 and x2 are independent, what do we look for in terms of statistical definition? Sukit.
The correlation or the covariance.
No, independence are not the same thing. It's not the same as correlation. Panat, what do we look for when you want to examine if two variables are independent?
Is it covariance equal to 0, like covariance of x1, x3?
No, that's what Suki said, and I said, oh, think about it again. Correlation and independence, are they the same thing?
No.
No.
I think it's you can write a product of PDF of x1 and x3.
Yes. Go back to the definition, right? Whenever the joint distribution between x1 and x3 is becomes the product of the marginal, right? Then these two guys are independent, all right? Being uncorrelated is verified by looking at the covariance. But independence, you go to the joint PDF, all right? Okay, that's one thing, all right? But then we have these results for, now we talk about a specific distribution. When we talk about Gaussian, what do we know? Independence and being uncorrelated, are they equivalent for Gaussian distribution?
They're equivalent in Gaussian.
They are equivalent in Gaussian. Okay, so now I'm gonna like put a scope in the Gaussian distribution because of this nice result. All right. Now I'm gonna step up to the definition of conditional independent. What does it mean by conditional? Conditional means so in the context of, if you verify that x1 and x3 are conditional, are independent, conditioning on which variable, right? So in this context, when we have a group of random variables, or equivalently when we have random vectors, so what we interested is, we would like to consider a pair, for example, x1 and x3 in this case, and we would like to see if they are independent, conditioning on the other variables. Okay, which means we would like to remove all the effects of other variable and then see if a pair, are they independent or not. Okay, for Gaussian distribution, we have these very important result that what? Theta what? X1 and X2, if X has Gaussian distribution, okay, the conditional distribution of x1 and x2 given others
Is also Gaussian.
Is also Gaussian. All right, that's one thing. This is from probability theory, and then that's x1 and x2 given others. All right, and when because of this fact that uncorrelated and deep independent are equivalent in Gaussian case, that's why we can examine conditional independent structure based on what? Based on conditional covariance of x1 and x3. Okay, because of the Gaussian case. Gaussian case. Now, maybe there's a bit much for now, but you can just listen to this as a kind of how the problem is formulated from the beginning, which means we particularly look at the Gaussian case because of these nice results about instead of having to go through PDF, we can just examine independent using the concept of covariance, right? But then in this relationship, in this problem inference that you would like to explore relationship between a pair, but when you look at this, you know, usually when your when your system is complex, when you study about a pair, it's important that you have to get rid of the effect of other people, right? You already know that simply looking at correlation matrix just give you the trend between, you know, a pair of variables. It doesn't suggest you about that these variable will have will be a cause of other variable, right? We have that example in the lecture as well. Okay, you can see in applications, this is kind of one common mistake as well, that people have a lot of examples on the internet that you can have, for example, I just need to find a blank space. For example, this is Thailand, right? This is Thailand. Of course, if you look at the solar power, okay, if I plot on the real axis, solar power, of course, on different locations. This is station A, this is station B. Station B is in the south, station A is in the northeast. Of course, if you look at the pattern, it is very natural, because that's the natural characteristic of the sun, that the solar power has a curve that it gets to the highest peak at noon, right? There might be some variation about weather uncertainty and so on. But then again, if you simply look at the correlation between solar power at station A and B, do you think it's high or low, Panat?
I think it's low.
It's low. Why do you think it's low?
เพราะมันแบบอยู่คนละลัติจูดลองดิจูดฮะมันเส้น
Okay. Maybe this is not a good example, but I will give you to. Actually, my plan is also to. I would like you to try this data set as well. I'm gonna have this solar power data set for you, either this homework or the next one. Okay. Oh, actually, the correlation is high because, as I said, because I mean the sun, the radiation is gonna have the curve that look like this all the time. There might be some variation, as I said, but if you just compute the correlation between the two stations, I mean, of course, because the time synchronized, right? At noon, regardless of the station, at noon, typically, I mean, we talk about like not like when you have in the rainy season, like most of the time at noon, this is where the radiation is maximum, not maximum. I mean, is high, right? So very likely that the correlation would be high between solar power from one and the second station. But that doesn't mean that you can use the information of solar power at station B to explain solar power in station A. Right? That doesn't make sense. Because I mean, station A and B are so far away in the north or in the south. It's gonna look very funny that, I mean, these two stations, you don't need to know about the cell characteristic or anything. You don't need to look at the spec of the latitude, longitude. Can you always use like one variable that correlated to another to explain? That is one common mistake in the causality concept, right? So what I have said is to emphasize the fact that when in causality learning, when we want to study interaction between a pair of two variables, we will get rid or remove the effect of other common variables. Sometimes we call it mediators. All right, so that's why what I'm saying, that's why people look at the concept of conditional independent. Mathematically, conditional independence is equivalent to conditional covariance, and that conditional covariance can be read by the zero pattern of covariance inverse. So this is mathematical fact. We don't go through detail, but if you're interested, it's everywhere, right? You can read from any textbook, any internet. Okay, that's why in this application, all right. In these applications, here's the following. You have vector x1 and xn. This is random vector. This is a group of random variable. Of course, from the data set, you will be able to compute the covariance, all right, sample covariance. And then from this mathematical principle that we know that when you get the sigma inverse, take the inverse of this covariance, the zero pattern in the sigma covariance inverse will reveal about conditional independence between a pair. In order to explain this, let me let me like maybe explain by this binary, by this like the color map. All right, suppose this is my inverse of the covariance, okay, and the one with the black area, the gray area, so the intensity of these cells is proportional to the magnitude of the entry in sigma inverse. So here is n equal 5. Okay, so which means with the white area, it means that my sigma inverse 1, 5 is 0. Okay, so in this cell, it means that it's non-zero. It has some non-zero number. Then if I have provided with this result, I can interpret that, oh, my zero pattern, zero inverse of entry 1, 5 is 0. Then I can conclude that my x1 and x5 are conditionally independent given the others, given x2, x3, and x4. So then with that, I can draw a relationship in terms of graphical model. So then I have x1, x5, right? x1, x2, x3, x5, and x6. Then now I can draw. In graphical model, you draw an edge, a link between two variables if they are dependent. So in this case, so if I see that the entry 1, 2, they are non-zero, which means they are what? They are independent. Okay. And what else? 2, 3. Okay. They are dependent. Okay. So what I said was a little bit wrong. And 2, 4, right? 2, 4. Where is the 4? X4 is here. 2, 4, they are dependent. They are conditionally dependent given the others. So when we have this as a graphical model, think about some complex system that some complex system usually is hard to interpret, right? But if the graphical model can represent their interaction in a simple way, it will allow a user to understand this complex system easier. All right. So that's why this is a motivation of a Gaussian graphical model. The problem is that if you look about some simple implementation that, okay, this is nothing difficult. I have data set, right? I can compute the sample covariance, and then I just simply take an inverse. And then when I take the inverse, this is what happened in practice. This is actually the sample, the inverse of the sample. It looks like this. So most of the time, these inverse that compute from the samples, they are not, I mean, their entries are not exactly zero. Okay, there's going to be some like light gray, right? This is also light gray. So again, now you have to come up with a way to threshold or to maybe to test statistical significance in the sigma inverse. That's why this freezes again. That's why the role of L1 regularization comes in, because now we can say, how about learning the sparsity from using the L1 regularization? Okay, so here okay, here I just cut straight to the formulation that they use. The meaning of X here is actually the meaning of sigma inverse. Okay, so here the cost objective here is a function of F inverse. That is has the meaning of log likelihood. Okay, this term again, this is the role of L1 regularization. So this is like L1 norm on the sigma inverse. Let me remind that an L1 norm of a matrix, suppose X is a matrix, right? So L1 norm, there's several ways to talk about the norm, but this is the norm we use. So you look at the ij entry, take the absolute value, and take all the sum. Okay. So because of the motivation that we previously say that zero pattern in the sigma inverse reveal the conditional independent relationship. So now when we formulate like sparse estimation problem, now we know that the sparsities are expected in the entries of sigma inverse, right? So that's why we use L1 norm of a matrix. So x here is the variable of sigma inverse. It turns out that this problem is convex, right? You see the sign of maximize here. That's because the original meaning of this statistical problem is to solve covariant matrix using the maximum likelihood principle. Okay. The problem is convex. Again, yet this problem is very well known. It's called graphical lasso. It's from lasso problem and graphical model. Okay. There's a term G lasso in R, and in the Python you can call the graphical lasso. I still don't see it in MATLAB. I'm not sure. All right. But as I said, the problem is convex. So if you know the tools in convex optimization, this problem is very simple to solve. So here's the results. Suppose I have the data, and then I know, suppose the ground truth of the sigma inverse is this. Again, in practice, the ground truth is never known, right? But in this example, I generate simulation data myself, right? So I can come up with a ground truth system, which means I have the ground truth one, all right, that I intentionally generate sigma inverse that has some exact zero, some sparse. And then of course, when I have the sigma inverse, I know my actual covariance is, and then I can generate, right? I can generate the Gaussian samples according to these covariance. Okay, what I did in this experiment is I generated with 30 samples. And then if I handed this data set for you, 30 samples. Then when you compute the sample covariance, now I'm going to use C, right? Sample covariance. And then you compute C inverse by just the matrix operation. And that's what you would get in the second plot. You see, so with the low sample, with the effect from this, you will see that these are not exact zero. So you can misinterpret from the result. All right, because you would think that, oh, x1 and x3, right? You may think x1 and x3, oh, the covariance inverse is non-zero. So they are dependent, conditionally dependent, but in the ground truth, they are not. On the other hand, if you apply the graphical lasso by using, of course, in the graphical lasso, just like any other sparsity learning, you have to specify the penalty parameter gamma. Here the detail of how to choose this penalty parameter can be studied further, but in this slide I just illustrate that if you use a sufficiently large penalty parameter like 0.8, you can see that they can extract the zero pattern of the sigma inverse quite well, quite agree with the ground truth. Okay, so of course in the past 10 years, people have people in the research community have competed in terms of algorithm, in terms of theoretical properties of this estimator, like bunch of papers in this area. You can just Google it. All right, graphical lasso. The next application is elastic net. It's actually the combination of L1 and L2 regularization we have seen before. So in the elastic net, the main loss function is quadratic loss. Okay. Now the penalty term or the regularization term is a combination of L2 and L1. Okay. Now you get different weight, and this weight is kind of complementary. So the user control the degree of alpha. If alpha is big, you pay more attention on getting a sparse solution. Okay. And of course, you have so alpha plays the relative weight. All right, relative weight of between L2 regularization and L1 regularization. But then user get to choose gamma. This penalty gamma. So now this gamma is going to be a trade-off between the whole regularization versus the quadratic loss. When gamma is 1 is lasso, when gamma is 0 is ridge regression. Okay. Why people are interested in the elastic net? Because of this property of ridge regression. I think I'm going to assign this question as a homework. All right. In the ridge regression, if two predictors are equal, I mean that's very extreme, right? But in a more practical way to explain this, if two predictors are collinear, if two predictors are dependent, all right, we know that we know that the concept of least square will fail, right? Because the regressor matrix will have rank deficient. Then, but I mean mathematically we can show that. That's why people use the ridge regression, right? When you have collinearity problem. But mathematically, you can show that when the two predictors are equal, the ridge estimate of beta 1 and beta 2 will be equal. Okay, which means when you get the solution path of ridge estimates, okay, you can see if a pair predictors are dependent by looking at the profile of a pair of regression. If they come and merge align, which means the corresponding variables are dependent. So so in this case, all right, that's why when you use the elastic net, you can get part of that feature from the L2 regularization. In this graph, I want to zoom in, but I'm afraid that the screen will freeze. Okay, it's not clear here because the values are very so actually there are two curves here, the blue and the orange. All right, that's a corresponding variable coefficients of beta 1 and beta 2. You can see that at the beginning they are slightly different, but suddenly when gamma is just about this portion, these two regression coefficients align. Okay, so you can recognize that some predictors are highly correlated. On the other hand, if you use the lasso alone, okay, so the lasso doesn't reflect this hidden meaning of the two variables. So in this graph, you will see that the blue and the orange one, okay, that's beta 1 and beta 2. They are not equal. They are not aligned. Okay, that's a feature of elastic net, and a good thing of the elastic net is that it's also like becomes available in any library. Okay. Mathematically, this again yet a convex problem is also strictly convex problem, which means the solution will be unique. So that's a good thing in terms of optimization. Next, the group lasso. Okay, the group lasso is an extended problem from a lasso in the sense that now the vector beta can be partitioned into blocks. Okay, so what we represent here, beta 1, beta 2, and beta beta k, these are blocks. All right. Previously in the lasso, you want sparsity in the entries of beta. Okay, what if you prefer a sparsity in the solution to appear in a block? For example, the block beta 1 is non-zero, the block beta k is non-zero, but the second block is entirely zero. So these result becomes desirable in structure sparse group. We call it group sparsity learning. All right. For example, like maybe you can have maybe you have k sensors. All right, k group of sensors. Like this group, like this station A. Okay, maybe let me talk about station. Like this is station label. All right, and in each station it has sensor 1, 2, ... P. Okay, each station it contains P sensors. For example, maybe temperature sensor, humidity sensor, precipitation sensor, and other things. Okay, so the label 1 to k here, let's say it's station labels. Suppose in your problem, you want to come up with a way to say, okay, of course, I'm gonna aggregate all information from k stations from all the sensors, right? But then people ask you, are there too many? Is it necessary to use all of them? Okay, so when you have this hypothesis that, okay, probably I don't need to use I don't need to use sensor from all stations. Looking at our Chula campus, actually our Chula campus has been installed with many PM sensors. In engineering campus, you know, in the area opposite to Payathai Road. Like for example, the Chula campus is not big, right? It's not big at all if you compare it to other countries. I'm not sure how I mean, what area do we have? But then let's say like you install a sensor to all the buildings, engineering buildings and faculty of art buildings. They are so close, right? So the problem is, okay, is it necessary to use all the information from all the buildings, like all stations? Now, this is come to the place where you can introduce the concept of group sparsity learning, because now I introduce this term. I want the statistical model. The screen freezes. I want the statistical model to detect that, can you extract this information to me, that can you select the station, right? Select the, is it appear? Okay. Can you select the station? Then what I would expect in, okay, so the meaning is going to be my beta 1 is going to be the coefficient of station 1, all right? So beta k is for station k. It doesn't appear. The problem with the screen. Okay, my beta 1, maybe you just listen. My beta 1 is a vector itself. Okay, my beta 1 is a vector in RP, which means I have P sensors. Okay, so if the problem, if the model, if the whole scheme return to me in the sense that the whole block of beta 2 and beta 3 is 0, just like in this, all right? It means that all the sensor from station 2 is not relevant, is no longer important to predict the response for me. Okay, so that's the motivation of group sparsity learning. And in order to frame this mathematically, right, if you want the whole block of beta j to be 0, then this is what we do. You compute, okay, so you're gonna have, maybe I'm gonna write like, this is the block of beta 1, this is gonna be the block of beta 2, so on, block of beta k. So what I'm gonna do is I'm gonna compute the norm of each block. All right, I'm gonna compute the norm of each block. So this is a vector in RP times K, because I have K blocks, each is a vector of RP. But now this is a vector of what? This is a vector of R. What's the size of this vector? Trung?
Okay.
Yes, okay. Then, all right, because I want the sparsity to occur in the whole block, then I use the sum of two norm. So this term is actually the what? The L1 norm, right? The L1 norm of this vector is the L1 norm of the two norm of each blocks. Okay. So in that sense, this is in mathematically we call it the composite of L1 and L2 norm. All right. So when gamma is large enough, right? So the L1 norm of this vector will be small. Some of them will be 0. Some entry of these will be 0. But then suppose the second entry is 0, right? So when the 2 norm of the beta 2 is 0, that means the entire block, which means all the entries in the vector beta 2 itself is 0. And that's how you get the group sparsity. So let me express these results. Suppose you have 5 blocks. Each block is a vector in R4. Okay, I vary the gamma. Maybe okay. So as of course, when gamma is small, all the blocks are dense. Okay. Now looking at when gamma is around here, you see that this block now becomes 0, and as gamma increases, okay, more blocks become 0. And so this is a curve between sum of the 2 norms. So that's the sum of beta j 2 norm versus gamma. And again, the meaning of this plot, let me emphasize again, the rows of gamma, when gamma is big, the parameter is sparser and sparser, which means these the gamma axis also suggests you about the model complexity. Okay, but it's just that when gamma is big, the complexity is low. Okay. Group Lasso, there's no command. I guess you need to write code to solve this convex optimization. Next one, and suppose I think it's the last one for the lecture. This is fused lasso. In fused lasso, the problem is motivated from the fact that you want the sparsity to occur at the difference of coefficients. Okay. So there's okay, let's see, maybe some illustrative example from image. Okay, from if you have an image, you know that each pixels in the image, all right, it has the intensity of the color in different degrees, all right, in RGB. So suppose that in the pixel 1 that I draw here, and in the pixel 2, now maybe I'm going to change the tone a little bit. All right. And then in the neighbor it's something like this. Okay. So Napat, what do we say when the neighboring pixels are very similar? That means that the image has a high contrast, or the image has smoothened out.
Similar, right? It is smoothed.
It's smoothened out, right? So let's say I'm not expert on the image or anything, but what I try to translate to you is that, okay, this is what you want to have in practice, and this is what we can formulate mathematically, all right? So what I'm saying is that if your goal is to smoothen out the image, right, it means that the intensity of neighboring pixels are going to be very close, right? Everyone agrees on this? You remember the intensity of each pixel can be converted into numeric values as well. All right, that's one thing, that's one application. Now you want, I'm going to use the term that you want some parameter of consecutive entries. For example, you want 1 1, you want 1 2, and you want 2 1, you want 2 2. These are neighbors, all right? You want parameter that are stay in the there are consecutive entries. They want them to be similar. In another scenario, in control system, a lot of times we want to develop a model with the parameter theta t, all right? The parameter theta that you allow it to be time varying, but then which means that you allow the parameter to be changed over time, right? Which means you're gonna model theta as maybe theta 1, theta 2, theta big, theta k. Your goal is to, of course, to estimate the model parameters as they are involved over time, but then you don't want the model parameters to be changing abruptly, which means if my theta here is 1, I don't want it to jump into 10 in 1 second. Maybe slightly change like this, 1.5, 2, and so on. You want model parameter to be slowly varying, which means if your goal is like this, I can say that mathematically you can take a look at the difference, right? You can take a look at the difference of consecutive entries, and the difference between two entries here should be what? Big or small? Sukit.
Small ครับ
Should be small, right? So this is some motivating ideas of the fused lasso. The key concept is you want consecutive entries of parameters to be close. So then you know that if you want them to be close, you want beta j and beta j minus 1 to be close, to be exactly equal. You know that the difference will be 0, right? And now that is a step of how you promote the sparsity. Instead of course, in Lasso, that the sparsity of the entries, now in fused Lasso, you want the sparsity that to be occurred for the difference of parameter beta j and j minus 1. So the fused Lasso has these feature. Sorry, not feature. It has this penalty term. All right, it penalizes on the difference between two consecutive terms, and then it also contains the original Lasso penalty, which means in this formulation, the user get to choose gamma 1 and gamma 2. User can design how much more attention you want to put on the solution beta. If you want gamma 1 to be high, which means that you prefer beta to be sparse, right? If you put gamma 2 to be high, which means that you want most of consecutive entries of beta to be close. So if gamma is big, what you're gonna have probably like the two of the entries, like these two one will be exactly 0, for example. Something like this. Entry 1 and 2 will be equal. Entry this and this will be equal. Okay, so this has been implemented a lot in signal processing. This is called total variation denoising. And yet again, the problem is non-differentiable because of the absolute value thing, the L1 norm thing. But the problem is convex, which means that, again, you can write your code to solve this convex optimization. Here, I would like to illustrate the effect on the solution. Gamma 1 is the penalty parameter on the Lasso term. Gamma 2 is the term on the fused term. The reason why they use the term fused is because, what does it mean, fused? True? True? Oh, where you from again, Trung?
Yeah, Vietnam.
Vietnam. Do you love fusion food? No. fusion food. The food that is mixed from multicultural, like many styles. No.
No.
No. Okay. For for example, we have Japanese rolls, right? And now Thai people have developed a menu, like they innovate a menu that they make a roll like a Japanese roll, but the ingredients are Thai, like Thai sausage. But they make a roll. So this is fusion food. So fused means you mix thing, you merge thing. So fused lasso refer to the term that these two coefficients become fused, become equal. Okay, in this graph, this is a plot where this is gamma 2, sorry, gamma 2. Okay, so we fix gamma 1 to be some number, and then we vary gamma 2. Okay, so what do we expect from this graph? Again, this is a solution path. How many, looking at the formula information on the slide, how many plots, how many curves in this, Napat, and why? Napat.
ยังไงนะครับงงอาจารย์
I'm asking, this is a solution part of the coefficients. I'm asking how many lines in this plot.
ผมนับได้ประมาณ 10
Oh, you don't need to count. You're looking at problem parameter, problem specification.
อ๋อ 10 ครับ
Is 10 because
10
is 10 because
10 predictors.
You have 10 predictors, so you have 10 parameters. So again, this is solution path, which means I plot beta as a function of gamma 2. Okay, so now if you see that, for example, this is where the blue and the purple line, right, becomes aligned, and that means the corresponding coefficients becomes equal. Okay, and when you increase, so that's a feature of the fused term, right? You see many pairs like the orange and the blue one here becomes fused at this point, at this point. All right, and now if we increase gamma 1, what does it mean? Gamma 1 is the penalty parameter of the Lasso term. So in principle, if gamma 1 is increased, what do we expect to get?
The beta will go to 0.
Right. Not only that, consecutive entries of beta will be equal, because you also increase the penalty on the Lasso term, which means some of the entries of beta will become 0. So that's why you see some of the coefficients here lies on the, lies on the 0 level. Okay. So fused lasso has a lot of applications as well. I will see if we can, if we have enough time to implement, like to try on some problem of the generalized L1. And but today's lecture is just, so we just introduce the concept of L1 norm. So the problem is, the main thing of how to apply the L1 regularization is you look at the meaning of your parameter in the model and to see how do you want the solution to become sparse. Is it on the entry itself? Is it on the kind of the group sparsity, or is it from like which function of the parameter? Just like graphical model, right? In the graphical model, the sparsity is not on the covariance itself, but is on the entry of covariance inverse. and then from there you formulate the problem in a mathematical way like that. Okay, I think I have I think I have listed the book. This is you see we use heavily on these guys. As I said, these are statisticians. They are mathematical professor at Stanford, and they also wrote this book. I think Wainwright is in Berkeley. I'm not sure. They have this particular problem, statistical learning with sparsity. Okay. Okay, so you can check out this reference for further studies. You have